Hello everyone. Today we will be learning a little bit of number theory. This is about forms of numbers. Forms of numbers. It is particularly useful for children in lower classes, let's say grade 5, 6, 7 and so on. But the seniors can also benefit from this. When I started learning number theory, I found that the idea of forms can be quite challenging. So let me spend a little bit time on this. We will do it using a problem. And at the end of this video, I'll give you a challenge question which you can answer in the comment. The problem is this, that suppose P is a prime greater than 3. This is the given data, and we want to show that 2p plus 1 and 4p plus 1 cannot both be prime numbers. So this is our goal. For example, if P is equal to 5, so it's a prime number greater than 3, then 2P plus 1 is 11 and 4P plus 1 is 21. See, both of them are not prime numbers. 11 is of course a prime number, 21 is not a prime number. We want to show this for all prime numbers greater than 3, not only for 5. We want to show that this is true for all prime numbers greater than 3. 2p plus 1 and 4p plus 1 is not both prime numbers. Okay, so how do we go about it? To do that, we will have to talk about forms of numbers. I'll give you an example. Numbers can be even or odd. This is based on 2, based on division by 2. Now what does that mean? Well, if you divide a number by 2, the remainder is either 0 or the remainder is 1. So sometimes when we do number theory, we represent even numbers as 2 times k. Here k is a constant number. So any even number can be written as 2 times some constant. And every odd number can be written as 2 times the some constant plus 1. So what does this 2k and 2k plus 1 tell us? It tells us about the form of even number and the form of odd numbers. Now let's do this form thing with 3 as well. We have done it with respect to 2. Now we will do it with respect to 3. So now based on 3, numbers are of 3 types. Numbers are of 3 types. What are those? Well, numbers that give remainder 0 when divided by 3, remainder 1 when divided by 3, and remainder 2 when divided by 3. So again, I'm going to write down the forms of these numbers. So numbers that give remainder 0 are 3 times some constant number. Any number that is divisible by 3 gives remainder 0, hence it's 3 times some number. If it gives remainder 1, it is 3 times some number plus 1. And when it is remainder 2, it is 3 times some number plus 2. So when we want to prove a theorem about forms of a number, then we have to use the form, the structure, not the number itself. So for example, if I prove a theorem for every number of the form 3k plus 1, then I have proven it to be true for numbers like 4, numbers like 7, number like 10. Every number that gives remainder 1 when divided by 3 will follow that theorem, because I have proven it for all numbers of the form 3k plus 1. If you have seen this before, then this is of course very easy for you. But if you are seeing this for the first time, you may have to think a little bit about it. Okay? Remember, form is what we are using, not the specific number. It's the structure of the number on which the theorem is. Okay? Alright, so let's now go ahead and try to solve this problem using forms of numbers. See, since the prime number is greater than 3, surely it is not divisible by 3. So that's something we have to be very careful of. P is not divisible by 3. Why? Because the only prime number that is divisible by 3 is 3 itself. So what could be the form of 3? Well, 3 could be 3k plus 1, that it could give remainder 1, or it could be 3k plus 2. So if I can show that 3k plus 1 and 3k plus 2 both are not prime numbers, then I have proven my theorem. Okay, so let's try to do that. So here is a proof. I'll do a part of it. You can do the rest and put the comment in the description. So we have prime numbers of the form 3k plus 1, 3k plus 2. We want to show that both 2p plus 1 and 4p plus 1 are not prime numbers. So let's work with the first category. Let's work with prime numbers of the form 3k plus 1. So this will be applicable for prime numbers such as 7, because 7 gives remainder 1 when divided by 3. Can you tell me a few more prime numbers which are of the form 3k plus 1? Okay, so now let's go back to this. We want to show if p is of the form 3k plus 1, both 2p plus 1 and 4p plus 1 are not prime numbers. How do we do that? Well, let's apply it directly. Let's replace p by 3k plus 1. See, we are replacing by the form, the structure. So it is 2 times 3k plus 1, which is 6k plus 3, right? You multiply it out as you normally do, and you add and simplify. And the second one is 4 into 3k plus 1, which is 12k plus 5. So see, we cannot say much about 12k plus 5. Maybe it is a prime number, but 6k plus 3 is definitely not a prime number. Why? Because 6k plus 3 is divisible by 3. So that's what we wanted to show. We wanted to show both of these are not prime numbers. So 6k plus 3 is definitely not a prime number because it is divisible by 3, and of course it's greater than 3. 12k plus 5 we don't know, but that's alright. We just wanted to know about one of them, right? Now we are at the very last case where p is equal to 3k plus 2 must be examined. So this is a little homework for you. You can put it in the chat. Show that if p is equal to 3k plus 2, then both 2p plus 1 and 4p plus 1 are not primes. What I mean is, both of them are not primes. One of them could be a prime number. That's fine. Show that at least one of them is not prime. Maybe I can write at least one of this is not prime. Okay, let's see if you can do it. This was a little primer on number theory for mathematical Olympiads, I.S.I, CMI entrances, and so on. You can check the link in the description for more resources, and we will meet you in the next video. Okay, thank you for watching.